Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video dealing with the lab exercise Environments of Deposition. So in the previous video we had been looking at clastic and carbonate sedimentary rocks, so now we're going to look at evaporite sedimentary rocks. Now, as the name suggests, evaporite deposits are the result of the evaporation of a body of water in hot, arid conditions, and of course this water can be either salt water or fresh water. Now, typically when you envisage this kind of scenario, you imagine a lake in the middle of a desert-like region, and you imagine the water evaporating away and just leaving behind the single layer of evaporites. However, that's not typically the case. Under normal circumstances, what will typically happen is the body of water that you're dealing with will be sporadically replenished, so new water will re-enter that basin, and that could be salt water or fresh water depending on the type of environment. Now, when this happens, obviously evaporite deposition will stop, but because you have all this new water, it's brought in a whole load of new dissolved ions within that water, and so when that water begins to evaporate away, it will then also lead to the deposition of evaporites. And because you have these repeated influxes of new water into your basin, you can actually end up producing quite substantial thicknesses of evaporite minerals. Now, in the case of freshwater environments, typically that replenishment event will often be a seasonal event. So you'll typically get heavier rainfall in, let's say, the autumn or winter and spring. So you would expect to see your body of water being replenished during that time frame, and then as you move into summer, that replenishment will stop and evaporation will take over. Now, when it comes to marine environments for salt water, typically what you have is a situation where you have a lagoon, which is protected typically by a reef or some other obstruction, separating it from the sea, and then that lagoon begins to evaporate away. So typically, if there's some kind of new replenishment event bringing fresh seawater into the lagoon, it's either because the barrier fails, so the reef breaks in a place, allowing fresh seawater to enter. It could be there's some kind of storm surge, so it's a weather-related event where water's literally getting pushed over the barrier into the lagoon, or there can be sea level change, and that sea level change can be quite quick in the event of something like an earthquake, or it can be quite slow, like in the event of, just general sea level change. Now, when water begins to evaporate, it actually follows a very regular pattern in terms of what minerals are actually being precipitated. So when you have anywhere between 100 and 51% of your water evaporated, nothing's going to really be precipitating out. However, once 50% of the water has evaporated away, that's the point where you're going to start depositing carbonate minerals. So you're typically going to get calcite or aragonite being deposited. Now, whilst evaporation is going on, nothing much is going to happen. You're just going to keep precipitating out carbonate minerals until you hit about 80% of the water evaporated. And at that point, you are going to begin precipitating out gypsum or anhydrite. So they're both calcium sulfate minerals. In the case of gypsum, it's calcium sulfate plus water. In the case of anhydrite, it's just calcium sulfate by itself. So typically, the hotter the conditions, the more likely you are to get anhydrite. Now, after 90% of your water has evaporated away, that's the point where you start getting the mineral halite precipitating. And then finally, once halite precipitation has begun, and once you've gone beyond 90% of your water being evaporated, that's also the point where you will then begin getting lesser minerals evaporating out. So these will be typically salts of other metals, so things like magnesium salts, for instance, or potassium salts might begin to make an appearance at that point. Now, obviously, because seawater and freshwater have different chemistries, it is going to lead to differences in the minerals which are being precipitated out. So the first thing is when you're dealing with a marine environment, so a saltwater environment, you are typically dealing with larger bodies of water, and seawater typically contains more dissolved ions. So because you have more water and you've got more dissolved ions, it will typically lead to much thicker evaporite sequences. Now, once, as just touched on, as your water's evaporating away at 50% carbonate, 80% gypsum, 90% halite, and then once you make it above 90% evaporated away, you're going to get these lesser minerals. Now, in the case of seawater, those lesser minerals are often going to be salts of potassium and magnesium. So the classic example is sylvite, which is potassium chloride. Now, in the case of fresh water, you are going to get the same basic steps. So you're going to get carbonates at about 50%, gypsum at 80%, halite at 90%, and then other minerals precipitating out at beyond 90% evaporated. The thing is that in a lot of circumstances, fresh water has less calcium and sulfate in it, and it also has less sodium chloride dissolved in it as well. So this means that the amount of gypsum and halite that will precipitate out of evaporating fresh water is typically lower than the amount you would get out of seawater. Another thing that you need to consider is that in most instances, the body of water itself that is evaporating away in a freshwater system is often much smaller than a marine system. So you're typically going to get a much smaller body of evaporite minerals forming, and because there's fewer ions in that system, there's also going to be less minerals precipitating out as a whole. Now, once you get beyond 90% or so having evaporated away, you are then going to get a different set of minerals appearing. So you're going to get at that point magnesium and sodium sulfate minerals appearing. You may get some interesting carbonates appearing. And arguably the most interesting group is you're going to get some boron minerals beginning to make an appearance. Things like borax will begin to precipitate out of the evaporating water. So you can see that depending on what type of water is actually evaporating, be it salt water or fresh water, you're actually going to end up with some slightly different mineralogies which will allow you to gauge, right, what type of water did I start with? And obviously that's then going to be useful because that is going to give you some information about the likely environment. So if you can see that, you have a layer of evaporite minerals, and you notice that there are some boron minerals in there. So once again, let's say borax. Well, then you can say, okay, this was probably a body of fresh water. So I'm probably looking at some kind of lake environment, lacustrine environment. I'm probably not looking at a marine environment of some kind. Now, another thing that people need to consider is that evaporite minerals will often only comprise a small percentage of the unit in which they are contained. And this reflects the environment in which they are forming. So in the case of marine evaporites, you are typically based in a relatively warm water environment, and the water depth is typically very shallow. So you can see you've met a couple of the criteria for the precipitation of carbonates. So it's not uncommon for marine evaporites to be associated with quite extensive carbonate deposits because they're going to form in the same kind of environment. So marine evaporites will often be a thin layer of evaporite minerals separated by a slightly thicker layer of carbonate. Now, in the case of freshwater environment, typically you will get a mixture of evaporite minerals and clay and silt dominated sedimentary rocks. And this is because your most common environment for freshwater evaporation is going to be some kind of lake environment. So you're going to have a river that will put water into your lake, at which point that water will obviously not only bring in the water itself and the dissolved ions in it, but also sediment suspended within that water, so clay and silt-sized clasts. And so as that water begins to come to a stop, it's obviously then going to allow the clay and the silt to begin to settle out of the water and form a layer on the bottom of your lake. And then eventually you will get to the point where the evaporation begins to lead to the formation of evaporite minerals. And then, as previously discussed, you will then have a replenishment of water into that basin. So then you'll get a new layer of clay and silt dominated sediments forming, then followed by another layer of evaporites. So evaporite sequences aren't just big thick layers of halite or big thick layers of gypsum. Typically it will be mixed in with other rocks. In the case of marine, so salt water, typically carbonates. In the case of fresh water, it will typically be clay and silt dominated sedimentary rocks. Okay, so now that we've looked at our three types of sedimentary rocks and had a discussion about what information those rocks can give you about the environment of deposition, let's move on to the lab exercise. So for part one of the lab exercise, you are going to be given 7 different lithologies for which you are going to have to come up with an environment of deposition. Now, for each lithology, there is going to be a table of data, which is going to give you some important information about your lithology. And then you are also going to be supplied with images of your lithology as well. Now, you will have to identify the environment of deposition for each lithology, and you will have to give a supporting argument for why you chose that environment of deposition. So if you look at question 3 here, it asks you what's the environment of deposition, and it's going to ask you to provide 3 pieces of supporting evidence. So you'll have to say, right, I notice that this rock has this feature, so that's why I believe it is that environment of deposition. Now, when it comes to each of the lithologies, you are going to compare information from the table of information about that lithology and the pictures to these 3 tables here. And these tables are going to give you the environments of deposition. So for each of environment of deposition, so in this case, we have continental environments. Let's look at something like glacial. Okay. So what kind of rocks and what kind of things would we expect to see if we were looking at a sedimentary rock that was deposited by glacial processes? So in terms of the environment itself, so we know that glacial deposits tend to form in elevated, cold, arid regions, and the sediment itself is being transported by ice. So in terms of the kinds of textures we might see within our sedimentary rock, we will see a range of class sizes from boulder to clay, because obviously a glacier is a big, powerful thing. It can move very large class and it can move very small class. We will also see that the sediment will be poorly sorted, because the sediment won't be deposited until the ice is melting. At that point, once the ice is melting, it's just going to dump all the sediment at the same time. So you're going to have a mixture of very fine clays and silts going all the way up to very large boulders. You will, however, see that the class will be somewhere between rounded to angular, typically rounded, because as the class are moved along by the glacier, they will often be rotated and rubbed against other rocks, which will cause them to become rounded over time. Then for your environment, you are then going to have the third set of information, which are sedimentary structures. So in the case of glacial deposits, all you're going to have is massive. So massive essentially means it's just pretty much a featureless layer of sediment. There are no sedimentary structures associated with it, really. You may get some kind of bedding, you may get some kind of layering, but that's not guaranteed. In terms of glacial environments, fossils, you wouldn't expect to find any real fossils, because it's not the type of environment where you're going to get much life in the first place, and then the chances of that life being successfully fossilized is very low. And then finally, you're going to get a description of the types of sedimentary rock that you often find associated with glacial environments. So you're going to get a lot of mud-dominated conglomerates, and that's a special type of conglomerate that we refer to as a tillite. So for each environment of deposition, you have a whole range of different factors that you have to be on the lookout for. And we have one table which is focused on continental environments of deposition. We have one table that's focused on intermediate, and we have one table that's focused on marine. Now, just going back to lithology number 1, how are you going to start to work out what your likely environment of deposition is? Okay, so the first thing is lithology number 1, color red. Now, we've already touched on what red colored rocks can mean in terms of how that red color can give you a hint about the type of environment you might be looking at. So if you're uncertain about that, you can go back through this lab exercise and you'll find it written down, or you can just quickly rewatch the first part of this explainer video, and that will also touch on what a red color for a sedimentary rock can typically suggest. So what other information do we have? Well, we know that lithology 1 is a conglomerate, and it has lesser coarse sandstones. Now, that's not really going to tell us too much, although conglomerates do tend to be quite high energy rocks, so that might suggest we are dealing with a higher energy environment. So we would be less likely to be dealing with an environment like a lake or the deep marine environment where energy is very, very low. Okay. Anything else? So boulder and sand size class, poorly sorted to sub-rounded, class of primarily granite, and the matrix of your conglomerate is a mixture of clay, silt, and sand size class. That doesn't really tell you anything. That's pretty much a description of most conglomerates. So, that piece of information isn't actually too helpful. Okay, sedimentary structures. Lithology 1 occurs as inclined beds, so it's layered, and those beds are at an angle. And the beds themselves contain massive conglomerates, so there's no features there. There's no ripple marks, cross bedding, mud cracks, anything like that. All you have are these inclined massive beds of conglomerate. Fossils, none. Okay, that would obviously suggest you're dealing with one of the more extreme environments, like maybe a glacial environment or something like a desert environment, maybe, where there will be less life around and it will be less likely that that particular life would successfully fossilize. And then finally, trends. Beds of lithology 1 become thinner as they progress from west to east. So these inclined beds of conglomerate actually become thinner as you move along them. So as you can see, there's a lot of information here for lithology 1. But as a geologist, what am I going to really look for that's going to help me focus on this environment of deposition? Okay, the red color is helpful. The fact it contains conglomerate is helpful because it tells me it's a higher energy environment. And then it's really these pieces of information that are going to really help me work out exactly what environment of deposition I'm dealing with. It occurs as inclined beds. There's something about that environment of deposition that's causing the beds to be tilted. And then the other thing I've noted is that the beds themselves are becoming progressively thinner. And so I'm going to focus on these two pieces of information because those are quite important to me. And so I'm then going to come up, I'm going to look through the table here, and I am going to try and find an environment of deposition that will result in inclined beds that become thinner. And on top of that, I am then also going to look for an environment which would be dominated by conglomerates as well. And so once I have worked that out, I am obviously going to then be able to name my environment of deposition. So I'll say it is X environment of deposition, and then I will give my three supporting pieces of evidence. I will say because the system is dominated by conglomerate, because the bedding is inclined, and because the bedding gets thinner. These are the three factors that I was looking for that allowed me to work out that that is the environment of deposition. And so you're going to do that for all 7 of the lithologies. There will also be other additional questions for some of the lithologies, and these will actually be designed to maybe try and point you in the right direction. So for instance, when it comes to lithology 1, question 2, it tells you asks you what does the red color tell you about the probable environment? Once again, that's just there to gently guide you towards a likely environment, versus maybe having you go off in the wrong direction. So you're going to do that for each of the 7 lithologies. So once you've completed that, you are going to then be moving on to part 2. So for part 2, once I eventually get there, because this is taking quite a long time, here we go. So for part 2, what we're going to do is we're going to use the information from part 1 to produce a map for the area. And so mentioned at the start of part 1 is the fact that these lithologies are Cretaceous. And so what we have is we have a situation where for each of the locations that were studied, there is a number next to that location. So number 6 obviously refers to lithology 6, lithology 2, lithology 1, lithology 3, etc. So what you're going to do is first of all, you're going to, if you want to, color in each of the lithologies that have the same number. Now, you don't have to do it, but it can be quite helpful because it can allow your eye to spot trends on the map more easily than if you just say, no, I'm just going to ignore that and just leave, leave them in black and white. So what you're going to do is you are going to try and draw boundaries between each of the different lithologies. And by doing this, you are going to be producing a geologic map for this area in the Cretaceous. Now, how are you going to draw the boundaries? So as you can see, there's an example map right here. So you can see on this example map, we have 3 lithologies, lithology 1, lithology 2, and lithology 3. And each of these circles represents a location where that has been studied. And for the Cretaceous age rocks from that location, we can see at this location, it was location 3, lithology 3 that was observed. At this location, it was lithology 2, and at this location, it was lithology 1. So when it comes time to draw our boundaries, how are we going to do it? Well, as previously mentioned, the first thing I would normally do is I would assign a color to each of these different lithologies, and I would just color in the circle and just say, right, I'm going to make lithology 1 orange, lithology 2 green, and lithology 3 blue. And that's going to instantly allow me to begin to see patterns. Now, when it comes to actually drawing the boundaries between the lithologies, what you're going to do is you are going to locate your boundary at an even point or an equidistant point between different lithologies. So in this case, you can see here we have lithology 1 and here we have lithology 2. So we know there's got to be a boundary in between them because we're transitioning from one lithology to another. And we're going to position that boundary at the midpoint between both of those locations. Here we have lithology 1 again, lithology 2, so we know the boundary is going to be somewhere between them at the midpoint. Lithology 1, lithology 2 again, lithology 1, lithology 2, etc. So you're just going to work your way along the locations where you have 2 different lithologies located next to each other, and that is going to be the location of your boundary. You will notice that I am not doing anything with these locations over here. That is because there is no other new lithology nearby. So for this location here, the nearest outcrop that had a Cretaceous lithology was this one here, and that was also lithology number 1. So can't really do much with the information from this point when it comes to drawing boundaries. However, as you can see, what I've done is the boundary continues all the way down, following the midpoint between where location 1 and location 2 occurs until I eventually reach the bottom of the map. So that's how we did the boundary between location 1 and location 2. And for the boundary between location 2 and location 3, we are going to repeat the same process. So you can see, right, here's location 2. We have all these location 3s over here. So we're going to go equidistant between there and there, there and there, there and there. And we're just going to keep repeating that process. And we're going to end up with a boundary that looks like this. And so, as you can see, it's actually quite a straightforward process. If you have enough information from your geologic mapping, you can actually use it to produce maps for an area for the geologic past, in this case, the Cretaceous. But you can do the same thing if you went to all of these locations and you identified rocks of, let's say, Devonian age. Well, you could use the same process to produce a map for the geology of the area in the Devonian. So it'll tell you what type of environments were present in the Devonian. So that will allow you to visualize what was going on in your area during that time period. So for question 1 of part 2, you're obviously going to be producing the map, and this is your map down here. And then you're going to be asked a question. So what is the direction of transport for the clastic sediments? And then what was the source of the clastic sediments? So you're going to have to think, right, once I've looked at the environments of deposition for each of the 7 lithologies, and I've looked at the map that I've produced, what is that telling me about the direction of transport? So remember, the direction of transport is typically going to result in your clastic sediments becoming finer, smaller. And so typically, environments of deposition that are close to the source of the sediment will often have larger clasts. And then as you move further away from the source of your sediment, the clasts will often get smaller. So you might see a transition from, let's say, conglomerates through to very, very fine rocks, maybe a shale or something. And so that's going to give you some idea about the direction in which the sediment was being moved. And that's pretty much it. It's a relatively straightforward lab exercise, but because there is a lot of information being given to you, especially in part 1, it can be quite easy to get confused, especially if my hints aren't particularly clear. And so if you do find yourself in a situation where you are trying to work out the environment of deposition, but you can't quite see what hint I was trying to give you to maybe point you in the right direction, please email me and I will get back to you as fast as I can to guide you in the correct direction and towards the correct answer. All right, thank you for watching the video, everybody, and have a good day.